Hey humans, I'm Aaron Rosenman, aka Ironcat, and I am back to talk more about how we're going to be evading Defender and other antivirus software and detective capabilities with simple changes to malware. Now again, we're all about humanizing the threat, and the point of this is that antivirus signatures are not necessarily going to be the answer moving forward, and that you have to have more defenses in that in your environment to be able to detect things that make it really difficult for attackers to change stuff in their malware that will cause them pain and difficulty and time. That way you're imposing cost on them. That's the deal. So we're humanizing the threat. It's people that have limited time and resources, and you're going to impose cost. Now let's pick up where we left off, and that is we had an old antivirus signature. Now that's not super cool, is it? So let's take a look at what we have now. So np computer status, or get np computer status, shows that we have a scan time of 125, which is the date I'm recording this. And of course, it shows that we have updated our antivirus signature as of 1/25/2023 as well. So now that is almost a year and some change in the future from the last time that we recorded. And we used that public repo, the Ironcat public repo, to test the defenses of the antiviruses at that time. So now we're going to, with this updated antivirus, check and see if it can now detect the previous version of Ironcat that we had. So let me copy paste here. Copy it from here. Paste it in here. There we go. Now, this is exactly what we hope to find, is on the event of it creating that file, it scans the file, and from here, it's going to delete it. So if we wait long enough, it'll delete that file. And that means that now the antivirus signature has actually been updated to detect this specific malware. And there it is. Now it's gone. It's disappeared, right? So with that gone, what can we do to understand how it caught up to those signatures and what it takes to evade them? Well, first let's take a look at virus total. So the old virus total detection had 41 out of 7, and it has a few things here that we're going to think are interesting. So I'm going to go ahead and kind of select. We have these 41 here. We'll open up a new tab for virus total for this for the future. But first I want to take a look at this medium detection. It says you can view the rule. This looks super fancy, like we're looking for some detections here that are interesting, except the reality is when we view that match, it's matching on something that this software isn't doing. How do I know that this software isn't doing it? Well, I made it. And so it's actually a completely false detection here. Same thing for the low detection. If we take a look at those matches, this again is just stuff that's happening on the system that's being ran as a sandbox, and actually a complete false positive. We can also go take a look at the virus total graph. So I'll go back here. If you click this in the top right and you're signed in, you can find the virus total graph and look at some of these entities. Now some of these, including this one, I think this may actually be right, but it doesn't talk about it. It says everything's undetected, and it's just an IP that it reaches out to. And we see that this domain that's been up for quite some time is actually considered 0 out of 88 detections. Now this one's completely false. I have nothing to do with Akamai on any of my infrastructure. That one's wrong. And then if we take a look at the rest of this, that's wrong. And this drop file is also wrong. We take a look and see what it is. I'm not really sure what that's even doing. So again, a bunch of false positives. It has to do with how this executes. However, signatures still caught it. Why is that? Likely because of the file hash. So this file hash, notice here, and starts with 6A, ends with D462. What do we do to change that? Well, let me show you. There is a tool that is part of the GitHub that was provided called Catamorph. And we run Catamorph against the version of Ironcat that was provided. Right, so that's IAI-PRV1. This is one that's currently on the GitHub. And we give it an output file that we're going to call new cat2.exe. Or even, let's just call this IAI-PRV2.exe. Great. Well, the very first thing you need to do is actually be where catamorph is, which it says it's there. Let's see, catamorph. Now it will do it for me. Let's do that. I'm going to go back. We're going to say /catamorph, / of course, because we are in Windows. Now let's give that thing a run. Now check this out. It looks at the MD5 of the current one. Okay, that was the current one's MD5, which we go look at MD5s, it'll match. That was not the MD5 on the virus total. And then it adds a key to it. So it patches the binary live. This is not fancy code, but it does work. And that's included in the GitHub so that if someone's simply detecting things through file hashes, you can modify it really quickly. And that's going to be a random key every single time. And now we have a new file sitting in here. And why don't we just go ahead and give that a test? So I'll get rid of this. We'll go find our new file that we have, and we'll go to virus total, open a new virus total tab here, and we are going to drag and drop the version 2 of that file that simply has a new hash. And when it checks the new hash, it's going to say this is brand new. This is what you see if that is brand new in general. So let's go ahead and confirm that upload. Okay, and this is going to take just a second. Not a big deal. It's going to do all this analysis on the file. It's doing quite a bit of stuff. The very first thing we want to do, and we see some detections coming, the very first thing we want to do is see this is not starting with a 6 and does not end the same way the other one did, right? So this is a completely new file by hash. While this is doing detections, what we want to be concerned with is what does this final number end up being? Oh my goodness, that number is not 41, it's 29. And all we did was change the hash. So what does that tell us with some quick public math? Well, what it tells us is that 12 of the signature engines, simply by changing the hash, did not detect it. So what we're saying is functionally that code is exactly the same up until the last few hex bytes. And now we have engines that people pay for, that people use actively in their environments, that now just simply can't detect it because that was the only way they were detecting it in the first case. And that probably means that they were looking at detections either from VirusTotal or from other vendors, kind of second party or second hand, and then taking those and adding them to a giant list of hashes that's ran every single time on your computer. And you imagine if we're looking at bad software, that hash list is getting bigger and bigger and bigger every single second. So that stuff's kind of scary. Now, let's see how Windows reacts. Now we have our Windows exactly same, nothing's changed. I'm going to copy that new file over. And again, look, we did get a detection, so that's good. VirusTotal is showing us that 12 of them are not doing so good, but Defender, at least updated Defender, must be doing some heuristics beyond the file hash to be able to detect that. That's fantastic. And now what I'm actually curious to see is what did it detect it as? And we can do that with get mp thread, really simple. And we can see that it detected the first one as the Revel here, and it's detected that second one as file cryptor. So another interesting note here is that though we did get detected twice, what's really, really interesting is that the first time it thought it was Revel, and simply changing the hash now makes it think that it's file cryptor. Really interesting there, and as we progress through this, we'll see how those differences help us understand exactly what's going on with these engines, almost reverse engineering the engines in the first place. So back on the desktop, that file's now gone, but what can we actually do to evade? Like, how much do we have to do to evade antivirus at this point? Does it have to be a completely new file? Well, let's find out. Let's go open up some of that source code, okay? And I want to show you the little amount required to be able to do evasions on the Defender capability. Now I'm in here, I'm going to go find that source code for this v1 from Ironcat public. Inside Ironcat internal, let's see, public release, here's some of the source code. So this doesn't come with the GitHub at all, and that is for a reason, okay? So we're in here in the source, here's our source code, and one of the things that I want to say we want to do here is get rid of the ransom note. So that is a big deal. So we take a look at this ransom note here. Welcome again, blah, blah, blah. This really looks like a Revil ransom note. So if I get rid of this and recompile it, I'm going to go ahead and spoiler alert you, it will still detect it. So let me show you what that looks like. So this ransom note is one of the things that's unique. So you imagine you're dropping this every single time. So let's make a copy of this file. Let's copy. We're going to paste it right in here. Paste. Let's main go copy. Rename test1.go. But let's now go ahead and modify this to get rid of this ransom note, because a lot of this is even kind of fashioned for the format after Revil. Ironcat wants your monies. Okay. So now we not only change the hash, but it's actually a completely different ransom note that drops as well. And this ends up being clear text inside of the file, even as an executable. Okay, so when we compile this, let's go ahead and build test1.go. We're going to use trim path to get rid of some of those detectable strings in there that identify your information, as well as can be identifiable information like strings that are clear text. And then we will see that we should have a test1.go.exe. Now, let's take that and see what we can do on the Windows system. So I'm going to drop test1.go in here on the Windows system. And again, we still have ransomware found. Which kind is it this time? File cryptor, not Revil. So changing that node actually does change that detection. So that's good to know. Can't just change the node, but it does make it think it's a different malware family. So we do know that some portion of Microsoft Defender's scanning capability has to do with strings. So there's other strings that are inside the executable that we need to be concerned with. Okay, so now we're back to the drawing board, kind of. But here's the deal. If you were going to encrypt something, what would you think was a bad maybe phrase to have in here? Do you think maybe it'd be the word encrypt? If we spell it right? Yeah, so it says encrypt kind of all over the place, like 12 times actually. It's used in the file extension. It's also used in the function names that we've created multiple times. Okay, so we're encrypting file. Those functions, unless you use a tool like we'll get into in the next episode to garble them, those functions are actually shown as strings that can be used as identifiable information inside the executable and part of what's used to detect it. So we can use a simple Control H here for find and replace. We're going to find encrypt, right? We don't have to do anything fancy here. Find encrypt. There we go. Spelled right again. Perfect. Spelled that right 2 times. Look at me go. And we're going to replace that with entropy. So like introp. Let's just call it introp. Cool. And when we're in here, what do we got? Replace one. Not forget that. Let's replace all of them. Okay. Really easy, right? Kind of makes some of the notes not make sense, but who cares? I don't care. Now let's compile that just like we did the other one, right? And that'll replace the old test.go or test1.exe. And we'll take test1.exe, the new one, and we drop that in there. And uh-oh, I don't see anything popping up, do you? I don't see anything at all, and I'm not trying to cover it with my face here. If I could move my face real quick, I would, but there's nothing. Let's check it out again. 0 detections at all. So let's go back to virus total, because that is like a super fun thing for us to do. And maybe, just maybe, we'll get a detection on run out of that thing, but let's go ahead and get virus total going on this thing first. All right, confirm that upload. Fantastic. It's going to do its thing. Let's get back to, okay, back here. Let's do the same thing we know we need to do while we're waiting for virus total. Let's go and put this in the root here. Provide my admin permission, of course. I would have it no other way. And now back in PowerShell again, and just kind of the prove the point here. Provides threat protection. Let's look at managed settings, cloud delivered protection, and real time. are both on. I got automatic sample submission off for now, just to provide us some cover while I happen to be doing this in the first place. Oh, I'm not a robot. I don't know why it thinks I'm a robot, and but I always fail these. I don't know if you fail them. Oh, I crushed that one. Holy smokes. Oh my goodness. So look, 6. All I had to do is change the strings that said encrypt to entrope, and now we're down from 29 detections to 6 detections. And in my RSA talk, I actually take the same version. I get it down to either 0 or 1 detection with some different stuff that's in that talk. But this is a little bit ridiculous. So what does that mean? That means that 41 initially detected, or 41 virus total engines detected it originally, just from it being around for over a year now, right? And then if we take a look, 29 detected it. So 12 missed it completely based off changing the MD5 hash. And then when we uploaded this, now we're down to 6. So I'll publish the difference of those lists so we can see which engines are doing what, because I think that's super interesting. And then just to look at the virus total graph from this exactly same file, let's see what it now thinks is happening. Well, it looks like that may be a different IP address, and we don't see any of the other information that we expected to see from that last graph. So these detections are not the same at all. Solely from changing some of the strings. So there's some other interesting stuff going on with Google Graphs. So I'm not just picking on Microsoft, I'm also picking on Google for how it does its kind of connections between executable files. Now, let's take a look back at the Hyper-V Windows test machine that's fully updated. Like I said, real-time protections on, cloud-delivered protections on. Now, let's go to that C drive. There we go, there's our test 1, and we're going to run our test 1 exactly the same way we did before. We're going to pass it the encrypt function and then that key. And there it goes, and once again we don't get a detection. So we do have, oh, that went super fast, right? And so as that catches up, we'll show that everything was encrypted. Oh, there's one detection, check that out. Let's see what it decided. And this is a completely different detection here. And unfortunately, it looks like it was a bit too late because the encryption had already ran, right? So that's not amazing. It's not necessarily what we want to have happen. And there's still files being written to disk because all those files changed. Also very interesting. Let's see what get mp threat gives us. Get mp threat. So here is something that I think is interesting. It says it caught this, did thread execute, says false. Well, we saw it execute, so that's not false. And again, here we are in a situation where the only way to be able to detect things is to test them yourself and make sure you have other detections in place. So that's the whole point here. Now, I will go over exactly what this executable does other than encrypt stuff because it drops a number of files that should get caught pretty consistently, and we'll look at some of the YARA signatures that do catch it in the next episode. And until then, happy hunting.